So hi, I'm Dave McAllister. I'm a technical evangelist for Splunk. I work in our what's called our app dev division, and we're focused on the observability world. So this is a little bit of an offshoot from the traditional IoT hardware panel, but we're going to look at how you can make sure the things you're working with, be they the applications, your services, or your just machine data are coming in, work well in this space. To start with, however, Splunk has a couple of sayings that every person is made up of 1 million points of data. So I thought I'd share a couple of pieces with you about mine. First of all, I am married, so I've witnessed that I do not read minds. Please feel free to ask questions in the Slack channel. Hopefully we'll get to them. If not, feel free to join me in the breakout room afterwards. I spent 10 years as a soccer rep. I am used to people disagreeing with me, so don't hold back. And finally, I'm owned by 3 cats, so I'm also used to being ignored. Trust me, if you've got 3 cats, you're quite good at that particular space. So in all these cases, we really are looking at a couple of changes that are happening in this environment. And they're moving from the old monolithic models of tightly coupled apps into more loosely coupled microservices and serverless functions, basically in the cloud, mostly called cloud native environments here. We've also at the same point in time seen the move from the dev throwing things over the wall to ops, to more communications, to being pushed closer together, and then actually falling into this space of DevOps, of SREs, of being able to work together. Shorthand, you build it, you run it for this. And so this is kind of where we're seeing the world evolve to. We're seeing this world evolve in edge-related computing. We're seeing this world evolve into traditional monoliths coming into place. We're also seeing this evolve heavily into the retail space. So to talk about this, though, I need to talk about a hot topic these days, something called observability. And basically, my favorite quote, you see, but you do not observe. Of course, this is Sherlock Holmes in the Scandal in Bohemia by Sir Arthur Conan Doyle here. But what it's really saying is that if you spend any time just looking at one side of your problem, you're going to be missing a tremendous amount of things that are possibly underneath here. So you need to be able to dive deep into what your data is telling you and be able to assure yourself that you're looking at all the possible problems, all the possible concerns. Another way of looking at this is, you don't dive headfirst into water without making sure how deep it is before you do this. So we need to be able to dive deep while being able to see everything that is going on. The TLDR for this, observability, is a quality of software services platforms that allows us to understand how systems are behaving. And for an engineering set, it's defining the variables in such a manner that we can figure out what's happening inside of that behavior. And these days, it's a signal to noise problem. Actually, let me rephrase that. It's a signal not noise problem for this. We have a tremendous amount of data coming in here. I used to be in the IoT space. In the IoT space, for instance, there's a possibility that by 2023, connected cars on the road will be producing 14 zettabytes of data to the cloud. It's an awful lot of data. There are 2 ways that we can look at bringing this data into something that makes more sense. The first is by bandpass filtering it, trying to cut down the amount of data by figuring out how to sample randomly or whatever to cut the amount of data that we can look at so that we can hopefully get a concept here. The other one is bringing the data in and then munging it together to a single gestalt so that we can understand what we're looking at with the ability to deep dive into any of those pieces and any of those functionalities. Observability is not one-dimensional. Going back to this multi-dimensional viewpoint here, observability is also a property of the system. It is not a tool. If somebody says they have an observability tool, you can take my advice, run away. You're looking for tools that let you understand what's happening inside the system. Observability is simply the word we use to describe how we look at what's happening inside of the system. It can consist of lots of things. It can consist of logs, metrics, events, tracing, anything else that happens in there. It needs to include elements of metrics as well as time. It needs to cross boundaries between your applications, your services, your disciplines, your infrastructure. And in today's instant gratification society, it requires speed. Anything that slows you down is bad. And it's not just monitoring. Again, observability is a system attribute. Monitoring is a verb. And while we'll talk about three pillars, there aren't just three pillars. There are lots of signals that come into play here. And they can consist of all sorts of things, including the traditional ones, but they can consist of profiling data. We have a customer who literally brings in their data from their Twitter feeds because they found that their customers always recognize something is going wonky before their system ever detects something's going wonky. At a previous site, for instance, we had over 1,500 core system. We had a single customer who was suddenly slowing down. All of our metrics looked perfectly good. 1,500 cores, our workload was up about 1.9%. But one customer is running slow, and he used to be running fine. We actually ended up drilling all the way down to the thread logs, which we stored for an hour, to figure out that we had had a simultaneous two problem occur. One, we had lost, somebody had misconfigured the system, so our elastic behavior was not happening on a customer by customer basis. It was now happening on a system-wide basis, and 1% wasn't enough to trigger it. And two, the customer had changed from sending us slow rates of large blocks of data to a very, very rapid rate of small blocks of data, and was filling up the ingest queue before we could deal with those two aspects. So we actually found this, but we had to go all the way down to the threads to figure out what was going on inside of that. This is an example that you're going to need signals that you have not even thought of yet. And by the way, those signals are not static. This is a system that is in constant motion. If it was static, then you could print off pages and stick them on your door and you'd be perfectly set. So again, you want things that respond to you as close to real time as you can get. So there are these three primary pillars of observability that get talked about. And they usually break down into metrics, traces, and logs for this. Shorthand, metrics. Do I have a problem? Traces, where is the problem? And logs, what's causing the problem? So each of these things actually drills deeper into our dimensionality problems here. So metrics, very honestly, the basic use for metrics is to tell you everything's working just fine, or to set off an alert when something's not working just fine. Traces help us determine what the headache pieces are that are causing our problems, as well as giving us some root cause analysis that lets us determine what pieces may be working together to possibly cause problems here. And then logs are the fine-grained detail. However, the logs are quite often dependent on the type of log that was written off. I have a former colleague who decided it would be cute to write all of his logs in Russian, which made it a real pain when we were trying to debug things and he wasn't around. So logs are only as good as the person who writes them off. So you'll also hear about events, and everything is an event, but events only exist if they're recorded and measured. To use the standard saying, you know, if a tree falls in the forest and nobody's there, and did it make a sound? Well, we need to be able to measure and record these things. And that measurement and recording also has different impacts on the style and nature of what we work with here. So metrics are compact, they're efficient, but they may not be sufficient, and they actually may not be complete. So metrics, for instance, help us understand the overall behavior by looking at what its relationship is to possibly historical events or seasonality type of events here. They are very quick to view and very quick to grok. Logs are full fidelity, but they're really bulky on capture. There's a company that unnamed, but does sort of the ride-share model, which produces 50 terabytes of log files per hour. So it's a little bit of a difficult capture when you're looking at that type of data inside of here. Traces are the new cool thing, usually called distributed traces. They tend to require work. You do need to instrument to be able to establish those pieces here. And by the way, traces can also be fairly bulky. So for instance, for a request-driven transaction in the average an e-commerce system, maybe somewhere between 10 to 15 log file items are written off, but there'll be 50 to 100 traces that are written off of that same set of data. So while this may be familiar, let me step through it a little quick. What a microservices architecture looks like here. What you're looking at is the basic page for amazon.co.uk showing all of the little microservices that work just with this page. And I'm sure that there's more behind this. My compliments to Martin Fowler for having this page up here, for instance. And each of these services in turn probably connect to other services. So for instance, an inventory service is probably talking to a database service. The also bought service is probably talking to a handful of other kinds of services. And so services then multiply, continue to expand. And we've got all these different pieces that need to work together very quickly to make that work. And what is powering microservices in many ways is this concept of Kubernetes, and particularly in the cloud. So Kubernetes is an orchestrator. Orchestrators basically automate how things get done here. And Kubernetes does this for containers. So it's the leader in container orchestration. It has multiple pieces. It's got sort of the Kubernetes orchestrator, the master node. It then has worker nodes. Inside those worker nodes are pods. Inside those pods are containers. Inside those containers are application services inside of here. Around those can be daemon sets. Around those can be monitoring capabilities like kubelets. And then we can have proxies that need to talk to the various networking structures. And we need to keep all these things tracked. So what Kubernetes is really doing for you is simplifying the ability to deploy this while adding a level of complexity to infrastructure that we also need to make sense of when we're looking at this fairly large environment here. Basically, you tell Kubernetes what you want, Kubernetes figures out where it can run it and how many replicas to keep it running at all time. So it takes a lot of the headache of matching to this model off of you. However, Kubernetes adds some additional pieces, not just the infrastructure functionality, but it adds ephemeral behavior. Containers spin up and down in seconds. It also has dynamic workload placement. Kubernetes will put things where it thinks makes appropriate, and it's left as an exercise to the viewer to figure out where that is. And those things add more challenges to our monitoring, to our in performance of distributed services. Therefore, the ability to pull that data from any source, which usually leads to open source type of data ingest engines being recommended, becomes incredibly important when you're looking at this overall large environment. Excuse me. And now, one of the near and dear things to mind. We talk about observability a lot, but observability should be a loop. So in machine control, which is where observability came from, the duality of observability is called controllability. Telemetry is its inputs, our logs, our traces, and so forth. So what we really need to be able to do is have our process, our app, and our infrastructure give us the information that's our inputs, this telemetry, allows us to observe what's going on and then take action. So they become controllable. That control can be manual or it can be automatic here. So in a manual approach, I'm going to notice that my commerce transactions are now taking 30 seconds. And I happen to know that thanks to a Google mobile survey, 5 seconds is a lost sale. I can now look at this and trigger somebody to say, go figure out what's wrong. Or I can possibly deal with it automatically. In a world of AI and ML models, we have more and more people making use of the ability to do things like automatic rollbacks for bad canary deploy, for instance, or be able to take an action based on, for instance, being slammed by a bot trying to break into a login environment here. These things are closed loop models. People are open loop models. But we need to get away from the concept that says observability is see something and say something to observability is see something and do something. So I'm actually very passionate about this fact that we need to close the loop on observability. Even when it's not a loop, we still need to close that loop. So why red? Well, as we've seen, there's a lot of complexity inside of this picture. There are lots of moving items. There are lots of interrelations that we need to happen here. There's actually a lot of not there now. As an example, in a Kubernetes environment, if a pod simply dies and you haven't taken the action to make sure that you've preserved the information the pod had for you, all that information is gone. It dies with the pods. Sure enough, Kubernetes will restart your pod, but you don't know what caused the problem unless you've taken the action. Likewise, containers spinning up and down have the same problem. And when we get into serverless, it's even worse. So the average startup time for a serverless cold start in Lambda, I think, is 400 to 700 milliseconds. Sounds pretty quick, but it's actually really slow because the warm time for that same Lambda is 38 to 45 milliseconds. 38 to 45 milliseconds is pretty quick. 400 milliseconds is pretty quick. And if it comes up and goes down in a second or less, you may not have even seen that it's happened. So we do have a lot of not there now. What we also need, though, is the simplicity and the ability to abstract our data out to get rid of some of that clutter. We talked earlier about how we have lots of different signals coming in. We have lots of noise in a sense. We need to make sense of that noise. So we need to be able to abstract down, need to aggregate the activities into complex and logical groupings here so that we can get rid of the clutter around here to see what's going on. At the same point in time, we need all that clutter because when something goes wrong, it's often in the details. So we need to be able to disaggregate all those pieces of information we just brought back together so that we can find specifically what went wrong, where it went wrong, so we can get through to the resolve and resolution, the resolution stage as fast as possible. So what is RED? RED's a spinoff of Google's Golden Signals from their SRE handbook. It was originally mentioned by Tom Wilkie, who came up with this concept around a set of signals that were for microservices. It turns out that RED actually fits into any request-driven system. Microservices just happens to be one of the better uses of a RED environment here. And it's made up of rate, error, and duration. So fairly straightforward, fairly simple structure inside of this. It doesn't work necessarily well for batch jobbing. It doesn't work well for streaming. But today, most of what we see our applications are in some level of request-driven environments. Be they e-commerce environments or be they simply pass-through environments. There is usually a start point and an end point and a unique identifier that goes along with each of those pieces. And so RED gives us that first level of simplicity of bringing together multiple pieces, 3 wide, that can show us a huge amount of information without us having to necessarily go any farther down. RED also fits into this multi-dimensional capability, the ability to look at multiple levels that are happening inside of my application space here. So rate, error, duration, you can align this to metrics, logs, and traces, but it gives me recognition of issues. Has something gone wrong? And recognition of root causes. Where did something go wrong? What went wrong? And so those 3 things given together actually move observability into monitoring at what I call the Chuck Norris level. Again, not see something, say something, it's see something, do something. So rate, pretty straightforward. Number, size of request on a network and system. It can be any type of transport mechanism, HTTP, SOAP, REST. It can be middleware, it can be Kafka, MQTT. It can be API calls. It can be the overhead of service messages like Istio or Linkerd here. Any environment that can fail on peak traffic is target for rate monitoring. And even though I did talk about it as a peak traffic model, keep in mind that rate can also be an indicator if it's too low. You know, Amazon near and dear to my heart here, but for instance, imagine Amazon Prime Day and all of a sudden their rate request on potential sales goes to 0. That's definitely a red flag of something going wrong. Even at the exact same level of being too high and having things throttle back. So rate is really important. And rate can give you a huge amount of information just by being able to disaggregate it a little bit. In this particular case, I'm looking at my requests are coming in at about 10.3 a second. I'm actually rolling these up over a 10-second period here, but I can also break it down and start looking at what it looked like and how it transpired. And now I can start seeing the vast majority of my time is spent somewhere between this 9.8 to 10.2. I have a couple of little peaks. I have a couple of little drop-off points inside of here. I can also look and see exactly what's happening in terms of the overall service endpoints. So I can see which of my endpoints are the most active, handling the most requests, as well as being able to break it down. In this one, I'm actually, again, showing you a 10-second viewpoint. I'm averaging over a 1-minute request, but I'm literally looking at every single endpoint that happens. The nice thing about Red and its aggregation is that I don't need to discard data to make sense out of this. Errors, everybody's dealt with errors, bugs, code failures, peak load bugs, communication problems. But errors are a little different. They require incredibly fast response times. They require point-specific responses, and you've got to be able to deep dive and hit high fidelity. And by the way, needs as soon as possible. And in fact, again, in the e-commerce environments, as soon as possible, maybe too late. You may have already started losing sales. It's there's some interesting surveys that point out that for every minute down an a major e-commerce site, you lose about $300,000. So you need to be able to resolve the issues as soon as possible in each of those categories. And errors, same thing can happen here. So in this case, I'm looking at, I've got this huge number of errors here. If you remember my requests were still pretty good, but I've got a number of errors here. And I can start looking at where my errors are coming in and where they're happening in terms of a timeline environment. I can, for instance, then drill into that environment and start looking at the endpoints that are changing and where the endpoints are. And then I can click on that and actually drill into it and start saying, okay, my catalog is driving my errors for this. So again, starting with a very simple number, I can suddenly drill into it and start figuring out where I need to look next to see exactly what's gone wrong inside of it. Finally, duration. And so short answer, its job is to bring things into causal order, put things in order here. Usually this is the domain of distributed request tracing or distributed tracing. And the nice thing is that we're now moving towards more open standards around distributed tracing. We started with open tracing, then Open Census from Google came out. Open Tracing and Open Census have merged projects to become Open Telemetry. And Open Telemetry is pretty much becoming the de facto standard moving forward, not just for tracing, but also for data ingest. And so if you haven't taken a look at Open Tracing, Open Telemetry, I suggest you take a look at Open Telemetry and figure out how it's going to impact the way you absorb data in the future for here. One thing to point out is that we tend to look at both the client side and the server side as being important. The client side is actually probably a little bit more important. That's the customer deciding to put his request in here. We tend to see more people tracking server side. It's simpler. It's easier to simply look at the things that are in the back room. But we need to kind of watch both the client side and the server side to make sense of this environment. Here, for instance, that same model for this, my latency running at a 99th percentile is running about 98 milliseconds. Not too bad here, but now I can also start breaking down and seeing what's happened in terms of the 50, the 90, and the 95. And then I can again look at it by latency, by endpoint, and see which ones are causing the problem. And each of those pieces, again, gives me another set of information. If this was live, mousing over this will show me catalog is still giving me my major set of nightmares for that. So why red? Well, interesting enough, in the world that we live in, there's lots of information, and red is really easy to remember. Rate, error, duration. I'm pretty sure all of y'all, if you walked out the door, somebody asked you what red meant, you'd know this. But it's got some nice pieces here. It helped us reduce decision fatigue. When you have microservice-based organizations, quite often you have a lot of different people building services or building a little set of services that are not the same group. And when we first brought them together to look at how we were going to monitor the data that we wanted to show on what was important, what we found was each group wanted something different. And so when we did this, we spent a lot of time going in circles where somebody goes, no, I don't need that, I need this. No, I don't need that, I need this. And what we determined was that by starting with red, we had a common set of environments that each person could then expand out to get their specific pieces. So red produced this decision fatigue. We made a decision, we moved forward and implemented red across the entire microservices environment, but we then let each team be able to drill into their unique capabilities as they wanted to do so here. That drove us a set of standardization and consistency. We now also had a common vocabulary that crossed those boundaries so that people could now exchange information. Hey, I saw something go wrong. Here's what it looked like. This team now knows what those pieces meant, and they can do their forensic exercise. In microservices, because microservices are very seldom deployed all at the same time, it's one of the advantages of microservices is update your service when it's ready for this. We quite often found that the service reporting the problem was not the service having the problem. And so red also gave us the ability to trace through this, usually using distributed tracing techniques, but trace through this to determine where the root cause aspect was actually occurring. And that made it a really important environment for us to be able to share information between actually geographically dispersed teams building microservices. So great standardization and great consistency. We also found in that closing the loop problem, red gave us a tremendous step up for automation. We now all had a common vocabulary. We could all agree on what something meant when it said something. So we didn't have to necessarily always depend on paging and flagging on calls. We can now look at this and say something is going wrong. Let's deal with the automation aspects. So for instance, push a microservice. We do canary pushes. Push a microservice out to this. That service solved a problem, but when it hit production scale, it literally started falling apart here. And we saw our number of requests drop and our duration and times go up. We didn't actually see errors. Service worked correctly, but we did see those two things. We implemented a runbook rollback immediately so that we could roll back the application to its last known solid state and then flag and alert somebody to say, let's go do some analysis and figure out what went wrong. So that gave us the ability, once again, to build a set of tools for our runbooks based on that common vocabulary we talked about earlier. And then, interestingly enough, it actually served as a really good reference, a proxy for user happiness. Again, referencing the Google thing, actually points out the Google study on shopping cart abandonment says that if a customer waits 3.6 seconds after clicking to the cart and it doesn't show up, they will abandon their cart. And at 5 seconds, it's over 100%. Basically what they're saying there is not only will they abandon their cart, they won't come back for this. And at 10 seconds, if they've waited that long and it's still not there, they'll actually go complain to their friends about your service on social media. And so looking at red, we can now see all the things that make up a user happiness model on an individual basis. Again, remember, we can always drill in and look at what happened to a request by request basis as well. But we can look at this and say, look, all the requests, we've got lots of requests coming in. They're all fulfilled in less than a second. Everybody's probably happy. The thing that's not known inside of this user happiness is, did they get the correct result? But I guarantee if they didn't, they'll let you know about it some other way as well. However, as great as red is, there's some gotchas that started creeping into this. And the first one that I really kind of want to talk about is a broad brushstroke. Every one of these metrics that we're showing, the rate, error, duration, can be influenced by something happening in one of the others. So we could, for instance, see that we've got a slow consumer. So we've got a duration slowdown. And that in turn could cause our rate to slow down for this. So rate may identify it, and while duration might not necessarily trigger that alarm, depending on how broad it is. But we may start seeing the requests drop off because the consumer is not able to keep up with it here. We can also see that you've hit a bandwidth limit, and that could also slow down your rate. And heaven forbid, if you have an error show up, I can pretty much guarantee your rate is going to suffer one way or another. Interestingly enough, this may not be a slowdown. This can actually be that your rate has gone through the roof because everybody is returning an error condition before they go any farther inside of that. Errors can be caused by a response time mismatch. We expect something to come back in a particular time. It doesn't happen. It can be actually generating errors that are being caused, again, by something happening at a duration level, even though the results being returned are correct. They may not be returned in a timely fashion. And the duration can be limits from infrastructure. I simply don't have enough bandwidth to be able to drive to the level I need. Or they can be the fact that nothing came back. There's an error again. So incomplete, incorrect, or non-existent results will cause my duration to have problems as well. So each of these pieces inside of a red environment can be affected by other pieces. And that's why you actually need to look at all three of these pieces inside of this so that you can truly understand what the overall pictures are. Fortunately, it's pretty easy to do a quick scan on rate error duration and actually take a look at what's happening in that case. So secondary challenge when we get into this, and this actually resolves into the traditional microservices, cloud, or whatever. It's not just the infrastructure, it's not just the application, it's both. And you need to be able to look at both at the same time here. In complex environments, the tools should be able to figure out how to help you with that. But bottom line, if you can't drill into it, don't bother. If all you're going to see are just the metrics that are telling you information, it's probably not going to be real useful for you to do that. So red can help you uncover a problem in microservices, under Kubernetes, across this entire environment here. But once again, we need red to be able to drive into that, the disaggregation aspect, so we can start looking at what each of the pieces mean and how each of the pieces impact the other sides. So talked a little bit about this, but there are two types of observability that we have in these services on requests here. The first one is the external customer view, and that view is singular. You know, if I'm shopping here, I want to know that my request went through, it didn't take very long, and it was successful. And it's a very individual to me. So I'm not at that point in time really caring did everybody else's work or not. The operator's view is over that entire workload. It's not just a request. They want to know how all the requests are running. They want to know how the rates are going and how the concurrency matches up here. And they need to map that to that infrastructure. The system resources and the components need to come into place as well, so that we can start seeing how our overall system is operating across this. So again, you need to be able to view your data from both a singular view, did it work for each unique individual customer, or from an operator view across the entire environment. So some philosophy. I ran a nonprofit for Stanford University called Philosophy Talk for a while. So I get to talk about philosophy. By the way, the hardest thing in the world is to get two tenured professors of philosophy to ever agree on anything, even if they're both in complete agreement. It's just not possible. Instrumentation by itself is not an answer. It may help you find an answer. So it's important to do this, but don't just say, oh, my code's instrumented, it's going to tell me all these answers. Part of the goal of the observability space is to be able to find the unknown unknowns. In general, we find that traditional monitoring looks for things we know could go wrong. This next level of going to the red space for observable nature helps us find things that we didn't know could go wrong. Metrics are incredibly powerful. We all know how to grok the numbers and what they're telling us. We know how to look at strip charts, but they may not be sufficient to tell us, again, all the way down into this. Again, we need to be able to drill into that model to be able to find out what's going on here. And by the way, cardinality matters here. So in this space for observability, cardinality is not just the data points we're recording, but how they interrelate. So the quick and dirty is I can write off a timestamp, a CPU, and the elapsed time for an application. But then I can also start adding other things to it, like what version was it running? What request was it operating? You know, all these different pieces. And every time I've added something, I have increased the possible set of data elements I need to be able to observe. In microservices, actually in most things in modern computing, we live in a high cardinality, machine language intensive world. Cardinality matters. Make sure that whatever you work with can handle cardinality without reducing the amount of fidelity that your code or that your environments have here. You want to observe the work, not the service. But you're going to observe the service anyway. But you want to observe the service as it applies to its workload. In this particular case, what that means is I don't just want to know that my systems are running and that my numbers are necessarily good. I also want to know what's happening for a request. I want to know how a request traces through. I want to know what my exemplars, my outliers look like. At the same point in time, I want to know that my service is working just fine. So watch how the service responds to its workload, rather than just watching to make sure that your service is running. Your goal overall is not this thing called observability, but it's reducing mean time to detection so that you can figure out something is went wrong, mean time to response so you can get things back to a stable environment, and mean time to resolution so you can fix it so it doesn't happen again. So those are the things that we really are looking at. Even though if we use the word observability, those are our goals: detection, response, and resolution. So to sum up, cardinality is more than just monitoring. Observability is more than just monitoring. It starts with monitoring, and it's really becoming more and more important that we go to monitoring at the Chuck Norris level. Red really does win for microservice-based applications, particularly cloud-native ones, where we don't necessarily know where things are at any given moment, and they can come and go pretty much as they please. Red really helps the observability of Kubernetes because it lets me look at Kubernetes levels of infrastructure, the underlying infrastructure itself, the application infrastructure, as well as the communication infrastructures, all in one place here. And finally, keep in mind that red sections interact in unique and interesting ways. So don't just look at one number, look at them all. Look at your traces, look at your outliers and your exemplars inside of this. And then finally, find the right tool to give you the clarity and insight that you need. There's no necessarily perfect tool for any single group. There are things like Prometheus that come into play in this space. There are lots of tools that can help you deal with this. But keep in mind that this is all around making sure that you can keep things working correctly, as well as making sure that when something's gone wrong, you find what went wrong and you fix it as quick as possible. With that, I'd like to thank you for your time and attention today. Feel free to reach out to me, Dave Mack at Splunk. I'm also on LinkedIn under Dave Mack as the 1,013th person to sign up for LinkedIn back in the day. So with that, thank you very much, and I'll turn it back over to you.